everybody. Maybe somebody should share the screen, the video. Erden, please, let us continue with the previous strategy of yesterday. So, okay. And if somebody else can share the video without paying too much for gigas, please do it. Okay. So now today we must talk about, we are in a kind of monographic part of this course. I explain you what I mean with this. Usually in the ancient, beautiful times of the best quality of Italian university, we had this some 40 years ago. Every course in the last years of master had a standard part. I mean, a part which has to be known by every student with an agreement of all experts in the fields. And then every professor was focusing on a part, on a specific subject, which he considered very important for possible research developments, or he believed it was useful in future. I mean, something which was not considered a common background for every student unanimously, but that the professor of that class believed that it was particularly important. And we called this a monographic part of the course. So this course we organized in this way. I started with something which, in my opinion, must be part of everybody's culture. Then we started, and we will continue, the training on an important computing tool. And I mean this console, but I mean could be every effective tool for getting prediction out of our formulas and models. And now I want to talk about a generalization of Cauchy continuum model, which is rather old. You see, it has been invented in 1884 in its most advanced form. And for some reasons, which you will understand, and I will try to explain you, this model, although it is very important in many applications, has been slowly rediscovered in the centuries, and only recently. And okay, this is the reason for which one has to be a little bit modest in pushing forward this, also due to my own scientific papers. Only recently, these ideas came back to the attention of a bigger group of scientists. But I think, and you will see with interesting numerical simulations, that this more general model is very useful in some novel mechanical applications. And we see engineering, possible engineering. Maybe in one of the last lectures, we will show you some specimen of new metamaterials which are governed by the general equations which we are presenting to you. So this is not only a mathematical game, it is also a very important prediction tool. I mean, you can predict the behavior of many new materials with this model. Okay, so what Piola wanted to do? He wanted to introduce a model capable to describe more deformation phenomena than those accounted for by Kochi. Okay, so we already introduced deformation energy W depending only on grad key. So we are limiting the expression of the total energy to this particular form. Okay, and so as we are making assumptions, particular assumptions, this means that we can predict only a specific class of deformation phenomena, and in principle we cannot predict every possible phenomenon. Okay, now let us recall our discussion about Cauchy first gradient continuum. This is, I think, very important. We claim that Piola did invent Cauchy stress before Cauchy. Actually, yesterday night, after preparing these lectures, I have checked what Piola wrote, that already Lagrange had introduced this concept. And I went in Lagrange book and I discovered that I had completely forgotten the fact that I had already read this. And in the Lagrange book version 1803, I found already something very similar to Cauchy stress. So, as usual happens in science, so the concepts many often have the name of the wrong person. Okay, but this is another story. So, in 1822, Piola introduced a stress tensor, and Cauchy published in 1825 a paper about it. Okay, Generalization is, he died recently. He was a very good friend of mine, found in the archives of the French Academy a manuscript having date 1822, claiming that Cauchy wrote already something in this date with the concept of stress inside, but we have no true evidence about this point. So I will not start here a war about who was the first man having inventing stress. I simply wanted to underline, that with variational methods, one invents things, novel, new things. So what I want to tell is that this search in the sources, so why looking for the first in doing something? One could say you want to prove that an Italian Lagrange or another Italian Piola did the job. Of course, this is a part of the story, but what is my interest, and you will understand this during the whole presentation, I will, in the next lectures, I want to underline that if you need to invent a new model, and I'm sure that in this audience, at least Erden wants to invent new models, right? So if you want to invent new models, most likely you must use a variational methods because in the history of science, in the history of mechanics, new concepts have been systematically invented only using variational methods. So this is the reason for which this search for the first inventor of the concept of stress is so important, in my opinion. So this is not a battle between nations or a desire. By the way, Lagrangian methods were invented by Lagrange, who never wrote in Italian because he wanted to be French. And he even changed his family name into French one, which is rather strange because nobody usually changes his own family name when he moves to another country. Hamilton and Green were British, and they based their investigations on, so Green and Hamilton based their investigation on variational principles. So this is not Tupin, who was born in Canada, and Midlin, who was American, based on variational methods, their investigations. So what I want to say, this is not a question of nations. You have a debate between two groups, and one group claims that everything has been invented using variational methods first, and I agree with this point of view. Okay. Anyway, we, in the previous lectures, deduced balance of force. We did not postulate. We did not postulate the law of balance of forces. We deduced it. Okay? So calculating the first variation of this energy and making simple integration by parts, we got, if you define capital P dW over dF, we got divergence of P plus B external equal to 0. P applied to the normal on the boundary. So this was in C star, and this was in the boundary of C star minus the part of the boundary of C star where essential boundary conditions were given. Okay? So for us, the concept of force is a derived concept, and we deduced it mathematically, and we invented it as a mathematical object inside a theory. The primitive concept in the postulation based on variational principles is the energy, which is also very abstract, but we assume that given a deformation, which is a kinematical concept related to something you can measure, you associate to every deformation a deformation energy. So even if I've not left this space, I will try to write the space which I need. I will try to write in blue here. So you have the deformation C, which is F transposed F. Okay, this is a measure of deformation. Or you can use G, which is 1/2 C minus identity. And you can measure deformation. Okay, then you associate W of F, the energy, which is stored in your body, in your small cube of body, when you have a gradient of placement F. And why we introduce C? Because W is 0 when C is the identity or as a fixed value. And if you remember, if you add to F a rotation Q, C is not changing. And this means that the energy depends only on the deformation measure. So the dependence of deformation energy is not on F, but directly, but on C. And we wrote this. W of F is equal W hat of C. And this we will need in some moments in the next pages. Okay. When you calculate the first variation of total energy, and I am simply recalling you what we already did, for every virtual displacement, you have the work spent by the internal deformation energy, I mean the variation of deformation energy related to the small variation of placement, and you have the work made by external forces on the first variation, so on the small variation of placement. So I'm running here a little bit because we already did it. Maybe we called this W. I now remember the symbols which we use, but you know, this is the first variation. So I wrote here the first variation of energy, and P is W over the F. Okay. And here I remind you contravariant and covariant notation. Okay. And you have the external work, and having integrated by part this expression here, we know that P internal can balance only some P external being made by a volume integral like this and a surface integral like that. But we will repeat this concept in bigger detail now. So I tell you the conclusion. We have proven that in order to have this equality, this one, P external can be made only by volume forces and surface forces, where force is something, a vector quantity, which is expending work on a virtual displacement. So force is defined by Piola and Lagrange as a mathematical object, a vectorial mathematical object, which is giving a work on a virtual displacement. So when I repeat this slowly, when you choose P internal like the first variation of total deformation energy, and if the total deformation energy is given by the expression W def, E def, sorry, when E def So under this assumption is integral over C star of W of only F. So when you have this assumption, you get a certain variation of deformation energy, this one. You integrate by parts, and what you get? You get that P int is equal to the divergence of something dot delta K, and the flux of something else on the surface dot delta K. So the only possibility which you have for balancing P int with external forces is this structure of external forces. This is a crucial point on which I want to discuss with greater details. So once given constitutive equations for deformation energy, one has a fixed set of possible external interactions that are applicable to the given class of continua. So what I want to say is that choosing W def implies choosing Px, possible Px. Okay, and this is not strange because Px has to be equal to minus P int for every virtual displacement. Okay, so you cannot choose any external force applied to any continuum. For certain constitutive equations for a continuum, you can choose only a specific class of external actions. Okay, now a large group of scientists, followers of Truesdell, Truesdell was a modern follower of Cauchy, claim that this is totally strange and wrong. Okay. However, already Piola had to explain this to his contemporary opposers. Piola was famous for several controversies with people from France. It is very strange. In that moment, the group of supporters of balance laws was concentrated in France, okay, and the group of scientists believing in variational principles was concentrated in Italy, but also in Great Britain, because more or less simultaneously Green was doing a lot of work in Britain. So you may think that my statement is strange. Okay. From a point of view of philosophy of science, the supporters of Truesdell believe that every ingredient of a model must be directly dictated by experiments. Okay, so Erden, maybe this point is crucial in our considerations. So they believe, so let us say, Cauchy supporters believe that every important ingredient of a theory must be induced by experience. Okay? So boundary conditions, they say, which are the suitable boundary conditions to give in a certain model, we must deduce out of experience. Okay? This leads to problems in logical coherence of theories. And this is a big problem which should be avoided. While in Lagrangian approach, you postulate something at the beginning of your procedure and you check the quality of your model at the end of your logical deduction. And then this is called falsificationism. And we will need to say in our paper that we are followers of falsificationistic philosophy. Okay?
Professor,
Yeah.
Professor, is that the rho when we try to define the M on the equation? Is that rho, right? Density.
Yes, density, mass density. Yes, yes.
Okay,
I will tell you this now. Okay. So, imposing that boundary conditions, deciding that boundary conditions had to be chosen independently of the other postulates of the theory is causing difficulties. Consider the case of perfect fluids. Nobody, we studied perfect fluids. We know how these fluids are made of. The deformation energy depends on the actual mass density. So I'm reminding you what is actual mass density. You have the mass of a body. It is the integral on the reference configuration of rho star dv star, where rho star is the referential mass density. When you consider a deformed shape C, you have the same mass is given by the integral over C of rho dv, where rho is the actual mass density. So remark that this is in general not time dependent, while this may depend on time. Okay, then we change the variable dv equal j dv star. So this is known that when you change variables in an integral, the volume element must be multiplied by the Jacobian determinant, which is the determinant of d small x with respect to capital X, or if you prefer, d key over the capital X. You replace in the formula and you get integral over C star of rho star dv equal integral of rho dv. Then you replace dv with j dv star. You change the variable inside rho. And what you get? You get that rho star is equal rho j, or rho is j minus 1 rho star. Okay? So in a perfect fluid, the deformation energy depends only on J. Okay. We know, because I used a quick way for deducing this but we can do it calculating the first variation and doing all transformations. We know that this assumption, which is very common and is the basis of every fluid mechanics course, okay? We know that this assumption implies, we know that with this assumption, one gets that contact force in Eulerian description have vanishing shear. So, perfect fluids can exert only pressures. Okay? Do you need experimental evidence? I mean, what is a perfect fluid? It is an invention of our mind. You cannot touch a perfect fluid. It is not existing a perfect fluid. So how do you get informations about experimental informations about which are the boundary conditions for a perfect fluid? I mean, the problem is, from a philosophical point of view, totally ill-posed, is completely crazy. Okay, we have an energy depending on J. We make calculations and we find that contact forces for fluids are only pressures. So you know that external Px must be only a pressure-like boundary condition, period. Okay, so it is a question of internal coherence of your model. And this is accepted by everybody. You will never read in a book on perfect fluids, even in Truesdell's books about perfect fluids, that you get these boundary conditions only by experiments. Okay. Therefore, we are already accepting that choosing the formation energy for limits the external interaction that the model can support. So to make it epistemologically well grounded, we postulate W of rho, and we discover that only phenomena with boundary conditions involving pressures can be described. So you will, if by chance you discover that a fluid is supporting shear at the boundary, then you say, sorry, perfect fluid model is not good, I must invent another model. So you must change everything. You must change the formation energy and boundary conditions all together. And then you will not believe it. This is a revolutionary position which has been violently debated when I presented it. So I think we must write this clearly in a paper. Okay? So a mathematical coherence condition limits possible interaction that can be modeled by a given continuum model. Okay? Very well. Now, let us generalize first gradient continua. Okay? So I want to motivate this generalization, but I will need another parenthesis explaining you what happened. So Piola chooses the deformation energy, which depends on F and on gradient of F. I mean, I was surprised when people attacked me at the beginning of my career because I wanted to study this class of deformation energy. Because it is very natural. You know, you want to do something more general. Up to now, you studied deformation energies depending on F, okay? Which is the next more complicated possible model? A deformation energy which depends also on the gradient of F. I mean, I don't that this is the simplest next more complex model. Okay. Now, if you want to build, okay, somebody tried to make this generalization for you, Dan and Serrin, without variational methods. It was a nightmare. Actually, they never succeeded without looking in the papers of the variational people and then ad hoc adapting their reasonings. Okay. Paul Germain, another French, but belonging to the school of variational principles, called these continua second gradient continua, and I think that this is the best way for calling them. Okay. So we will do in the next lectures a slow series of reasonings. Our aim is to understand which external interactions can be supported by second gradient continua. So I want to make this clear. We know that for perfect fluids, you can have only pressures. Okay. Now our aim is if I have a deformation energy which depends on first and second gradient of F, which kind of external actions can I apply on my continuum? So which are the external interaction we can imagine as applied to a second gradient continuum? This is not easy. We need some mathematical, how to say, we need to develop some mathematical tools. So I will go very slowly in deducing this general properties, the general properties of external interactions applicable to a second gradient continuum. So let's go to the principle of virtual work. The first variation of deformation energy plus the work made by external interactions must be equal to 0. Okay, so once you choose this is the first choice to be made. Okay, then this equality, the fact that the first variation of deformation energy plus the external work has to be equal to 0 for every virtual displacement, constrains the possible form of Px. So what we have to do, we have to integrate by parts this to see how Px can be done. Okay. In order to hammer in your head this, I go back to the example of first gradient continuum. Okay. This is what Erden agreed with me yesterday, that it is the best way to repeat this another time. Okay. So you calculate the first variation of deformation energy, it is here. Then, if you remember, integrating by parts, you get that this volume integral is equal to this volume integral, something dot delta k, plus this integral, which is dw dfn dot delta k. Okay? And if you assume that, let us imagine that you are stubborn and you believe, okay, just 1 second, somebody's phoning at my door. Stop the registration, Alessandro.